Hello everyone, thanks for coming. And so today we are going to talk about Swift deployment monitoring and performance analysis using Swiftacular. Basically, I should say Swiftacular because it's spectacular, kind of. And that was the original author's thought when he gave the name to the project. We will show how we reached the conclusion that switching from regular Swift disk backend to BlueFS will benefit in terms of is beneficial in terms of performance. So let's let us introduce ourselves. Adrian and David. We're working in the same team. Basically, not anymore. Adrian is working in the monitoring team, and I'm working in CI Forge team. But once upon a time, it used to be the same team. Okay, so this is the agenda for today. This is the agenda for today. We will see what Swiftacular is at all. Basically, it's a tool that allows the deployment and monitoring of Swift. Then we will continue describing more in details about the core functionality, how to deploy, what is deployed, what is not, what cannot be deployed with Swiftacular at this stage and needs additions where Swiftacular needs additional contributions. And then we will describe how to monitor Swift performance using the ability that we added to Swiftacular. And then this part is a preparation for the performance considerations and conclusions, where we will explain the architecture, how disk backend in Swift works and how BlueStore is architectured. Ceph BlueStore is architectured. Then we will show the benchmarks we performed and what we observed during the benchmarks and on a monitor, on a Swiftacular monitor. And then we will reach the conclusion why BlueStore as a high performance and memory efficient storage is beneficial as a backend to Swift. And you are invited to download this project, to git clone this project and run the benchmarks according to these slides, just to verify our findings. Okay, and we will be grateful if you will do it and ping us then we will also explain how development environment, how Swiftacular enables the development environment to facilitate development of Swift, which is deployed in a multi-node way. Because currently, when deploying DevStack, using DevStack, you have all-in-one Swift, right? And here, it is very easy to change code on any node and see what's going on a cluster level. Okay, so just go to Swift storage one node, change there, restart services, and observe what's going on the level of the whole cluster. Future work, there is a lot of work to do. a lot of work was done, but a lot of remains. And final remarks. And virtual microphone to Adrian.
Okay. Hey, hello to everyone. I'm Adrian. Well, before going to more deep into the Swiftacular project, I'm going to talk about some key terminology. I don't know how many people are familiar with Swift. They can. Okay. A lot of people. Great. So I will just go fast on this slide. So I will keep it. I will just go further because we will explain with more details what we have in Swiftacular. So many people seem to be familiar with Swift. Well, Swift is an open stack project that is open source. It's basically for distributed object storage. We have. I mentioned some of the capabilities or some of the features that it has, but well, you can visit the documentation to see everything because it has a lot more. I mentioned global cluster capability because you can use it to a lot of servers and very well distributed. We mentioned middleware architecture because you can add new functionalities to plugins that you can attach to Swift. Partial object retrieval because we can fetch all the information in one block, but also in chunks using Swift. And we provide also a control panel that you can access via browser. It's just a basic introduction. Okay, so these are the components of Swiftacular of the project. Once you deploy it, what we have there is proxy nodes, several storage nodes where the proxy nodes are redirecting all the requests. We have the observability services, in this case with just Grafana. We will go with more details about it. And in the rest of the services, we have Keystone for the authentication with Swift and package catch. Well, we are not using it very well here like it works in Swift, but we mentioned in the deployment. So we are doing the deployment via backend using the Libvirt as an example in the project. And you can see the virtual machines that are running in the right side in this project, and the networks that are created. Okay, people that how many use Ansible also here? A lot of people. Everyone knows about Ansible, so I'm gonna go deeper about it. We mention it here because it's part of the project. Why it was used, playbooks or roles are really simple to understand and to write. It's agentless. All in Ansible is done via SSH, so it's even better. And the requirements of the project: background Libvirt, Ansible, and internet connection. So we have a note here that we mentioned background as the provisioning and the network setup and the setup of the ECC keys to access. But you can give a try to run deployment into bare metal machines. Maybe there are some required changes into the networking stuff because in the background is everything automated. You just need to do background up and you will have everything. So maybe for bare metal, you just need to change a little bit the provisioning steps. This is how you get everything running. Everything is very well specified in the project. You just need to clone and go inside the cloned project. You have a script for installing the requirements, which is everything that you need for running it. Right now it's working on Ubuntu and Fedora, and well, we are trying to make it run at all in Linux. The next step is to execute.
Even edit it on Arx Linux.
Yeah, I'm using it, so I was struggling a little bit for that. So the next script is for preparing the storage nodes with all the compiled BlueStores. David will explain better how it works. Then we provision the machines with another script. It's where we have everything related with background to create the background bus, to set up, to create the networks. And then the last script is for deploying it. And here is where we have Grafana. We are using, I'll explain better later, we are using Grafana, that is a library to automate the creation of the dashboards. Well, I mentioned here about the network, it's what I said in the previous slides. Okay, for the monitoring, we are using Grafana. I guess that people use it here also Grafana. Visualization, a dashboard platform. And we are using Grafana, that is basically a very nice library that Grafana has It uses JSON.NET language that is basically an extension of JSON, and you can use it as like dashboard as a code. You can write code and deploy in a very automated way dashboards and visualizations. So that's what we are using for the. We are including, we will show better, two dashboards in this case. Host overview dashboard that is using very common metrics to understand how the Swift works with all the workload using Performance Copilot. And another dashboard for metrics related with the storage. How are the objects, the distribution of the objects, all the information about it. Okay, this is an example of the first dashboard. It has a lot of visualizations. With Swift, we are creating a lot of test containers. So we just took one test container as an example here. It has 3 visualizations. We can see how is the distribution of the objects, the size of the database when we are creating it. This was done with a script that creates as a workload some objects to check how Swift is working. And the other one is the dashboard I mentioned with Copilot. Those metrics are the ones that we show while we were generating the objects and doing some test performance. You can check all kind of information there, not just about CPU and memory, but also about XFS and inodes. I think that's all from my side. Thank you.
So as Adrian mentioned, those panels that were added to the dashboard are very important because, as you probably know, since there are wide audience that were about Swift and probably about performance, the XFS file system, okay, it uses at least 2 inodes per object, and if, for example, the common problem is many small files, right? Because it blows up the memory. So we can see this from every storage node how much memory is used by inodes, and it's not the only one. You can even see the bit trees of XFS and collecting a lot of metrics. And if something else is needed, it's very easily extendable, as Adrian said. So let's deep dive into how we used all this stuff that Adrian was talking about. So we have here the learned architecture of Swift. We will see just the XFS, okay, just 3 layers here. So XFS is writing to objects as files on XFS file system. We have in this deployment currently by default it can be easily changed, but we are creating one file of 5 gigabytes. On every storage node we're creating 2 files of 5 gigabytes. A loopback device, MKFS as XFS, and we have basically 2 disks for every storage node with XFS. So what disk file is doing is writing extended attributes, metadata for those objects, and the objects are stored on those 2 disks as files. Okay, that is, I guess, known by everyone, but just to be on the same page. Then the object disk file, which provides basically the disk file writer, and disk file reader, is operated by object server, right? Obj server.py file, which externalizes the endpoint, and basically when objects are written to the Swift backend, it comes to port 6000 something, and everything propagates from that endpoint request to XFS file system. That's how it works on a code level. Any questions regarding the previous slide? Good. What is Ceph storage backend? Ceph storage backend writes objects the Ceph storage backend that is used currently with Ceph is called BlueStore. It's block your store. Okay. Previously, I don't know if you heard about file store. Okay. Previously, Ceph used file store, which had also many issues. We will show them on one of the next slides. It was replaced several years ago. Objects are directly written to the device. Metadata is written to RockDB, okay, and RockDB is using is running above BlueFS, which is a very small file system that also uses this block device as to store blocks, okay. So they are sharing basically. The BlueStore shares this block device between the objects and between the blocks of BlueFS that stores RockDB metadata. More information is here. This slide was taken from Sage Whale's talk in 2017 about the whole architecture of Ceph. What we did is basically we wrote BlueStore utility, okay, small BlueStore utility on Ceph is written on C++. So this code basically creates a BlueStore. So in order to compare apples with apples, if previously here the Swiftacular deploys everything on XFS file system, which is basically a file of 5 gigabytes. We did same thing with this device, okay? But it's 2 gigabyte device, okay? Just not 5, but it doesn't matter because we are not exploding it. And here is the code creation of BlueStore. Everything that you see. I'm not used to this one. Sorry about that. So basically, the code is showing us how object store is using BlueStore, the API of BlueStore here, okay, at the edge here. So we're asking to this snippet asks to create BlueStore, and here we have the write object, read object, and mounting the BlueStore. Okay, very easy to using this utility to write objects to the BlueStore. Oh, forgot to mention that this is related to what Adrian said before here. Since compilation of Ceph is pretty time-consuming, it was to create beforehand the background box with precompiled Ceph in order to set up cluster faster. Okay, so Ceph is precompiled already when you are cloning, when you are running, after you are running this script, and it is located on storage nodes, on every storage node. Okay. Next, what we did is basically we wanted to do some benchmarks. Let me skip this file, this slide. And about this slide, it mentions the previous work that was done with replacement of storage backend of Swift disk backend. The change was abandoned. The implementation is here. Slides are here. They are very descriptive, so you can read them. And here is the page that describes everything. So basically, disk file in this implementation was also changed to there was implemented some key value store, okay, in this change, and you're familiar with the.
I was working on it.
Oh, you were working. Oh, nice to meet you. Okay, I thought why it was abandoned, and if I'm guessed the right reasons for so we'll ask you later. Thank you. Let's go further. Okay, so if we think about those problems, right? Then the next question that comes is, okay, Ceph went the same way. They had file store that had pretty the same problems. Okay, they also writing twice, and there were inconsistent performance, and also when listing files, according to the file store also used XFS. Okay, so it's very analogy. It's the analogies to what is done currently in Swift, and the question is, why not to use BlueStore? Okay, but before doing anything, right? When you are steering the wheels right or left, we need to do some checks if some vehicle is not approaching from left or right. So we did some benchmarks, some simple benchmarks, and here is a benchmark. First of all, the BlueStore object benchmark from 4 kilobytes to 1 megabyte, and you see the times. Okay, and if we compare the times, it's 1/3 of storing same block size, same file sizes on XFS. Let's see it. Okay, you see the times here. For example, for 4K, it's 300 or something USEX, and here it's only 700. 3000 VS 700. Okay, it's even X4. Okay, and this happens through the all basically blocks. Even with bigger blocks, it becomes worse on XFS. Okay, I don't know why this slows down. We had no time to investigate. There is a lot of work to do yet. So just anticipating the question why this happens. Okay, maybe some caching, maybe, I don't know. Okay, so okay, let's see now what happens with metadata. Okay, we've done with files. Okay, files, BlueStore much better. X3, X4. Now let's check what's going on with saving metadata. RockDB. By the way, every benchmark we have a code here. It's in Swiftacular. Okay, so you can simply set up cluster, SSH to storage node, and run benchmark. Okay, for XFS and for BlueStore. That's it. Very easy. It will take 1 hour to prepare everything and 10 minutes to run benchmarks. Okay, and I really encourage if you run it, ping with your findings if they are differ from what we found. Now. This is RockDB. Okay, RockDB, you see it's linear, okay, and here it becomes exponential. Okay, but that is expected there, right? Because That's how RockDB works. But you see that for sizes under for value lengths less than 16K, it has very decent time, and it's less than writing X attributes of the same size. Okay? If you compare here, for example, okay, we have attribute size of 8 bytes, 200, almost 300 usecs, and here we have 17 usecs. Okay, way better. It's an order of magnitude better. Now, and in addition, look at the performance here, right? It is far from linear. It's glitchy, and we have spikes, and we have the growth began much earlier than for RockDB. Much earlier. The reason, by the way, why this happens is explained on this slide. I don't have if we have enough time and if the auditorium will be free, but we can talk about why this happens. It's described here, but we can. It's just hints why it is here, why it happens. And by the way, why Swiftacular is great, because we observed it on Swiftacular Grafana page. Okay, so that's why we enjoyed to have those dashboards. Okay, next. So are we assuming that all this data is valid? I guess that we have persuaded you that XFS should be replaced by RockDB and by BlueStore, by writing directly to the device as BlueStore makes, and attribute updates should be replaced by RockDB updates. And the question then is how exactly to do it. We can do it very simply. We can go to disk file py and replace every set extended attribute call by simply calling to Python code that at the constructor to set up RockDB per disk and store attributes in RockDB like this. And we can use our BlueStore utility to store files on BlueFS. Okay, that is pretty easy to. That is pretty achievable. We can call from Python code an executable that is written on C++. It will add another from 2 to 10 USEC overhead until it reaches the first instruction in the BS util. Okay, depending on operating system, depending on CPUs, depending on everything. But for example, per 1 million blocks, 1 million objects, it will add an overhead. This approach will add an overhead from 2 seconds to 10 seconds, right? Which is probably okay if taking into account that disk py is not running basically wrapped by service, right? That is approached via API call. So it's a valid approach. But then the question is, why not to rewrite the whole thing? Disk py server VY by entirely as a service that simply to take the code of BlueStore and puts there a listener, and that's it. Okay, and then we will save this one as well. So that's the question, and here we have reached. We have basically some implementation of this, which was not pushed yet. Okay, it's a not big change, pretty small change, but maybe we will end up here, and I will be happy to hear thoughts. So that's it. Now, how development environment looks like. We have time. No one is coming for our salts. It's very easy using Vagrant command to create SSH config and then to install on VS Code the remote SSH plugin, and then through the remote window I'm just in 1 minute able to open the Swift code, okay, on storage node from user libpython package Swift, okay, and also able to open the Ceph code, okay, that is pre-configured at the configuration at the beginning, the scripts that Adrian was talking about, when Vagrant box was created with precompiled Ceph. It takes something like 1 hour, assuming that you have at least 8 CPUs and 20 gigs of RAM to spawn the virtual machine. Otherwise, it will take more. Everything is written in README, by the way. The minimal configuration, the minimal requirements, etc. Yeah. So then it's possible to create patch and commits. Everything is nice. This is how our CI looks like. In fact, it was looking like, because eventually when we have added Swift as Ceph, we had to increase the memory, and our CI server has only 32 gigs of RAM, and at least 64 is required in order to operate, so we need to find another server in order to run this smoothly. This is how our project page looks like, which epics we're working on, what is done, what is in progress. That's basically it. Future works, all items marked with idea bulb on previous pages, and also we have not mentioned the Erasure code support, which also needs to be addressed, and Swift over EVSSing. This is another project at another scale. So it's kind of not Ceph BlueStore, but something that is called object disk. This is a simulator, something non-existing in nature yet. That's it. Final remarks. So we found it very useful to use Swiftacular to deploy Swift in multi-node with multi-node topology, and to change code and to observe after changes what's going on a more serious cluster. Not production grade yet, because we are using disks that are simulated on files in both cases, in both BlueStore and CephFS. So we need basically to deploy on a real bare metal machines, okay, just to verify it. But chances are probably that it will be okay, because even though maybe when you have operating system that manages that file, there is some chances, right? But we'll verify it, and this verification step is crucial before continuing on this replacement full steam or making 1% guarantee that it is required, that it is beneficial 100%. Basically, another, I have mentioned this one, so I mentioned everything important. That's it. The batteries, no. Okay, references, okay, and you.
Apologize for this. This is for the slides. I open a review but still not merged. So this is a mirroring from GitHub to Gerrit. You will have an error, but you can access to the project anyway. In some minutes, the slides will be available. So I apologize for that.
Okay. If you have any questions.
I think the Ceph guys are also working on this new optimized OSD daemon for NVMEs. I think it's called Crimson. Are you also considering to test it on that instead of BlueStore later?
We did just what we did. So any additional things are welcomed. We have not. The BlueStore basically can be configured for cold and hot with the SSH and spinning disks, and there are a lot of configurations. So it is very premature. We just found it and showcased that it works to research in this direction. But any ideas to research and any additional hands here are welcome. Yes, definitely.
Right.
Thank you.
David, one question.
Yeah.
So you did not have to touch any code in the proxy? The proxy component. So there is the object server and the proxy.
We haven't touched any code.
And so maybe you're using the rsync replication from the proxy. I'm just wondering why the user code will not work.
We haven't tested the replication. We have not tested nothing. It's just very basic one. Okay, at this stage. But that's why this work a lot. But it's very promising, and it's backed with Ceph, right? Because the RocksDB is a very solid project, and Ceph BlueStore, there is a community behind it. So, any other questions? Okay, awesomeness. Thanks a lot.
Thank you.
So, basically, the problem, right? Of course.
No, we don't use that. We just reuse what we have, what was in Swift. And we are just using as an extra discipline performance provider. And we export the method. This the one for objects or the one for performance?
Lower than I really expected.
For the objects.
So the
Sure.
thing, then I started to work on that.
Something like this, and I found that this part of the presentation that would permit it exporting. You have to do all that things.
We made internally.
I will show you better what we have in the code, because
migrate to object server from real files to the volumes. I had BlueStore bit. But then, so that was working pretty well. But then, so that's
we are using
I know that
this
is
one,
also public.
but here you can see the connection to the data source.
So we brought OpenAI.
Everything is with PCB.
You know that?
We need the performance
So we
point.
built a-
So it's
a-
putting metrics with that.
which had some things that the customers really wanted, which is a
Unix is like fits Prometheus with queries like this.
Swift is eventually consistent,
Mhm.
and some AI workload and machine learning, and not just like some shapes of Swift.
And-
Put an object and immediately you have to answer what it is, translate it to
all the
a data
stuff.
server, and it was
So you
a second behind,
have
so it pulled all the workload.
this check.
Yeah.
Because the other one is like
Yeah.
to do
Internal infra.
So yeah, paying for another tool.
I'm gonna we built a whole.
Not like a names,
We are paying.
yeah, to
If you are eliminating eventual consistency, you need to.
yeah, in this case we are not using
There's a
Yeah,
trade-off,
it's
right?
yes, it's true. It was a lot.
It's for us it's a nice approach. This one is specific case of the system.
Different problems.
Yeah.
And they are still busy.
Something.
Basically, that's what I was on my free time.
No, because he was testing just the performance of all the concepts. All the things that are, let's say, part of Swift were not tested.
Because I was imagining how.
That's what I did basically, because
That's
they,
the guy that knows
they,
more. Yeah, because I know more about the
getting this
he's the
deployment
one deeply in that
and
part, yeah.
putting Grafana stuff
Yeah,
there,
from part
it
of
was
the
done as a part of
Yeah, I
the
see
project.
That's good. Great job to do.
I will try, I'm waiting to immerse it.
Okay,
Also,
you
you have the
explain.
slides also, you can see.
Your small changes.
We lived through the same thing. I wish you luck with the continuing of this. Yeah.
So you're located in Paris?
No, I'm in Brest, offices in. No?
Yeah.
Okay.
I don't know. I know
It's a small
it's
place.
small.
It's a very small place.
Hello.
Thanks for this presentation. Small thing that I quite didn't get, and probably have no infinite conflict on it, is that how you can implement like replication. You don't have to give like in theory how you can do like replication with the BlueStore rsync.
Basically, it should be seamless unless I don't know some underwater obstacles, because the replication the replication is comes through the replication service, right? So it asks eventually it is propagated, and you can say if I'm wrong. Eventually it propagates to disk file. So if you are replacing something under the disk file, then it will work. And if we replace the whole service, then you need to add replication endpoint.
You are using Swift already?
Yep.
So you know there are two ways to replicate currently?
I'm only aware of one, so rsync.
So rsync might be a little difficult because it expects that it will have a normal file system in front, like completely normal file system. So you could use ssync. That's what we did for a kind of similar project that you mentioned, so that it will speak to the disk file directly, and it does not care what's the implementation behind. So ssync would be one way. Also, I think that was required for erasure coding.
Async is required for
Yeah, I
erasure
think
coding?
because rsync will just take the file like you want one copy and you take
not-
it and copy it. And so we were already using async for erasure code. So maybe you could use it if you want to have both, like erasure code and BlueStore. I would probably go that way.
And you had it before, then you migrated to async.
So we had a very standard previously, a very long time ago, rsync and mirroring, and we needed to save money, and we were asked by the bosses, no,